In this video, we will compute a surface integral of a vector field over a surface which is given parametrically. So here the surface is part of a cone. Z squared is x squared plus y squared, but only the part whose z coordinate is in between 1 and 2. And we want the outward pointing normal for the orientation. So here's the cone, and again we only want a certain part. Let's say here is z equals 1. Then we only want this part of the cone. And we want the outward normal, so at any point we want the normal vector to point outward, away from the middle of the cone. So if you look at the picture, you can tell that this will be, you could also describe this as the downward pointing normal vector. The normal vector, in order to point outward, will have to have negative z component. So, okay. First, since we said we want our surface to be described parametrically in this particular example, we should first parameterize this surface. So, I'll color it green. So I'll write this in green. I'm going to parameterize it using polar coordinates. So instead of the usual u and v, I'm going to call my variables r and theta, since they're going to mean the same thing as in polar coordinates. So x and y will just be the usual polar coordinate equations, r cosine theta and r sine theta. And z, if you look here at the equation for the cone, z is the square root of x squared plus y squared, which in polar coordinates, that's the same thing as r. So here we can just have r for our z component. And if we like, we can factor out an r since it's in every component. And what are our bounds here? We have r is in between 1 and the square root of 2. And theta goes all the way around. Oh, sorry. This should be 2, not the square root of 2. Z is equal to r, not r squared. So these are the bounds of our parameterization. Now when we go to substitute things in the integral, we need ds. So we need to write what ds is for a parametric surface. And ds is this cross product of the partial derivative vectors. Or possibly in the other order. I think maybe we'll want to do it in the other order, but we'll see after we compute it. Remember, we want outward pointing normal vector, which we said in this case also means downward pointing. So we'll compute this cross product and we'll make sure the z component is negative. If it's not, we'll just add a minus sign. Okay, so we need to compute what this is. So in this case, r theta is, so we take the theta derivative everywhere, minus r sine theta, r cosine theta, 0. taking the r derivative, we get cosine theta sine theta 1. And taking their cross product, we get r cosine theta, r sine theta, and let's see, minus r sine squared theta minus r cosine squared theta, so minus r. And again, if we want to factor out the r, this is cosine theta sine theta minus 1. So that's what we want. Remember, to have that normal vector pointing outward, we need the z coordinate to be negative, which it turns out to be in this case, so we're in good shape. Okay, now let's actually compute the integral. So, we'll want to, for the bounds of our integral, use the bounds for the parameterization that we wrote earlier. So r goes from 1 to 2, and theta goes all the way around from 0 to 2 pi. Now for f, we look here. In our parameterization, we have x, y, and z, and we'll want to substitute here for x, y, and z the functions from our parameterization. So for f, we write minus x minus y and z squared dot, and below we have ds. It's this cross product times the differential, and below we have computed the cross product. It is, I need to make some space here, r cosine theta, r sine theta minus r, and dr d theta. So let's do the dot product. We get minus r squared cosine squared theta minus r squared sine squared theta. So let's factor out the minus r squared minus r cubed. Of course, cosine squared plus sine squared is 1. So this simplifies. We'll pull the minus sign out to just r squared plus r cubed. And there's no theta, so there's no harm in doing the theta integral first. It just gives us a factor of 2 pi. And we'll just do the r integral at the same time. We're going to get 1/3 r cubed plus 1/4 r to the 4th from 1 to 2. And what do we get here? 2 cubed is 8, minus 1 cubed is 7. So 7/3 plus 2 to the fourth is 16, minus 1 to the fourth is 15. And let's see, what do we get if we combine these fractions? Common denominator here will be 12. So 7 times 4 is 28. And 15 times 3 is 45. 2 over 12 is 1/6. And 28 plus 45 is, what, 60 plus 13 is 73. So our final answer is minus 73 over 6 times pi.